In the previous video, we had just showed that we could think of the derivative as a linear approximation or as a linear function and rewrite our standard definition of the derivative with that in mind and get a slightly different version of it. In this video, we'll explore that in a lot more depth. Now, if you're keeping score at home, this reduces exactly, this whole argument reduces exactly to the limit of f of a plus h minus f of a over h as h goes to 0 is equal to the derivative, m. Okay, but it's a slightly different way of looking at it. And this way extends. Now, how does this extend to higher dimensions? So let's look at this again. The limit of 1 over h times the quantity f of a plus h minus f of a minus f prime of a, h, that has to equal 0. In other words, the difference between the derivative and the difference quotient as h gets closer to 0 is 0. Okay, again, just sort of an algebraic way of reformulating this definition, the original definition, but the advantage here is that we have a slightly different conception of things. All right. This, as we said before, this is a linear function. Now, in the previous page, it was a linear function because this was a line. But if you look at it, mh, it's a linear function that if I graphed mh by itself, it would be a line through the origin with slope m. And that actually fits our definition of linear function that we've been using in this course, which is sort of the more, the sophisticated, not high school definition of linear function, the analysis definition of a linear function. So we have here that this is a linear function. And which linear function is it? Well, it's the best approximation. The best approximation to the function at the point f of a. Okay, so this is kind of interesting. Now we know, if we go back to here, maybe if we want to come up with a linear function, well, we can just come up with some sort of linear function which approximates these vectors at some particular point. So maybe our linear function here, for example, would have vectors pointing like this and like this and like this and all sorts of straight. So the further I get away, the less they match up. But at this point, the vectors for the derivative point the same. Okay, that kind of makes sense. For this guy, we have, if I'm going to do the derivative at, say, this point, well, maybe I want a linear function, and for this particular case, you can imagine that a linear function would be a tangent plane, and that would be a linear function. Okay, so we can conceptualize the derivative now. Instead of the slope of the tangent line, it's the, well, what it is a linear function which best approximates the function at a certain point. Okay, now there's a reason why we spend so much time doing matrices and linear functions, because, and the reason is because we can represent a linear function with a matrix. So we're going to say that it's a linear function, remember it's a linear function of h, so if I had my derivative, f prime of a, f prime of a is going to equal some L times a. Now, this is cool because if L is, if f is a function of one variable from R to R, then then A is just a scalar, and A is just a scalar, and L is just a one-by-one matrix. In other words, L is equal to m, the slope of the tangent line. But if A happens to be a vector, and L happens to be and A happens to be a vector, then all we have to do is make L some matrix, and it gives us A. So that's all, I think, kind of cool. And the question then is, what is this what is this matrix. And I think the book does a nice job, algebraically you can see why it is what it is, but I think now we have some conception as to why it should be a linear function and why we can represent the derivative by a matrix. So the matrix, actually I'm surprised the book doesn't call it this, but the matrix is called the Jacobian matrix. And it's the matrix of all the partial derivatives. So it's the partial derivative of f1 with respect to x. This is the partial derivative of, well, maybe we'll call it f sub x because it's the first component. So again, the first component, then this would be the partial derivative with respect to y, and this is the partial derivative of x with respect to z. I'm doing a 3 by 3 matrix here. Partial derivative of f sub y with respect to x, partial derivative of f sub y with respect to y, partial derivative of f sub y with respect to z, and etc. So all these partial derivatives, these are going to give us a matrix. Now you may ask yourself, but these are all going to be functions, and functions, it doesn't make it a linear function, because if these are all functions, a linear function, these have to be constants. The entries have to be constants. But at a specific point, and that's what we're defining here, we're defining the derivative at a specific point, each of these is going to take on a specific value, and that's going to give us a bunch of constants. And then this vector, this matrix full of constants, is the derivative at the point A. Okay? At a different point A, we're going to have to plug in again, and we're going to get a different matrix. So, and that makes sense because we have a different tangent line, we have a different best linear approximation at every point. So this matrix, and this is called the Jacobian matrix, again, is just the matrix of partial derivatives, and that's what we're going to, that is the derivative in higher dimensions. Okay, so let's do one example just to make it a little bit more concrete. In the interest of time, we'll cut this video off right here and do the example in the next video, part 3.